Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have an interesting geometry problem, but there's quite a bit of algebra involved here as well. Go ahead and give the problem a look. I've described it as best as I can. In fact, let me use some lines here on AE just to indicate that it's a segment. And here as well, this is the length of the side AE. Okay, this problem is a little bit more involved. So it's going to take easily 6 to 8 minutes. If you know what you're doing, it will take a little bit less, but you might have to wrestle with it and play around with some ideas. Make sure you have careful representation in this problem, which is a huge part of calculus. When you're in calculus, you're going to have some word problems. Might not even have a diagram like I drew here for you. You would have to produce that diagram carefully by following the instructions. And then once you can represent the situation properly with an expression or an equation, then you can begin to do calculus stuff. Well, we're not in calculus yet, but being able to represent a situation with an expression or equation is pivotal, and it's a pre-calculus skill. So let's test your skills here. You can pause the video, give yourself, like I said, 6 to 8 minutes. If it takes longer, then maybe you can learn from your mistakes or see where you got stuck so that you can improve and get faster. If you did it faster than 6 minutes, bravo. When you're ready, you can unpause the video, see how we did it here. Now, we have that ABDE is a rectangle, so this side is not necessarily equal to this side, but opposite sides are congruent. So that means that this side BD is the same as this side AE. And we're also told that triangle BCD, that's this triangle here, is an equilateral triangle. Okay. And the perimeter of this entire shape, ABCDE, is 42 inches. Now, one thing to be clear about is that the perimeter is only the outside. Right. So let's start labeling some side lengths here. We're going to call this X, which means this is also X. Is that hard to see? I believe that is pretty difficult to see. Let's use a brighter color here. If that's X, then this is also X. And since this is an equilateral triangle, all of the sides are the same, which means that this is also X. Maybe I'll draw it inside the triangle so it shows up clearly. This is also X, and this is also X. However, when we're considering the perimeter around this shape, we're not actually going to use that X at all. Looks like someone covered a couple fries in like way too much ketchup. Anyways, these exterior sides on the left and right, we can call these both Y. Sure. And we know that the total perimeter along the outside, ABCDE, is 42. So how would we formulate this? We would say that 2y, because we have the left and right sides, plus 3x only. That's this x, and this x. Again, we're not including this side BD in the perimeter of the overall shape because it's not on the outside. And this is a total of 42. All right. Now this is true for parts A and B, this constraint that the total perimeter is 42 inches. We need to find the length of the side AE. Well, AE is the value X. That would maximize the area. This is huge. We want to maximize the amount of space. So with a limited perimeter, we want to make it as big as possible. How do we represent the area of ABCDE? Well, this is a composite shape, right? Composite shape. This is a rectangle plus a triangle. So we need the area of the rectangle as well as the area of the triangle. The area of the rectangle is very easy. It's just going to be x times y, right? As you can see, we have a length of x and a width of y, so the area is simply x times y. But what about for this equilateral triangle? Well, for that, if you don't already know the area of an equilateral triangle given its side length, here's an opportunity for you to figure it out. Hopefully you were able to figure it out if you didn't already know it. But if you do have it memorized, that's great. It's very helpful, it's very quick. Let's give a discussion on how to find the area of this triangle very briefly. So if we have an equilateral triangle, that means the angles are all 60 degrees, right? Because all the sides the same means that all the angles are the same. So if we were to split this triangle down the middle to represent the height, we could then find the area of this triangle by saying base, which is x, times the height, but we don't know the height yet. So splitting this down the middle creates a 30, 60, 90 triangle. Aha. And in that 30, 60, 90 triangle, let's cover up this entire base side. Half of this base side is right here. That's going to be x over 2. And you should remember this at least from a 30, 60, 90 triangle. If you don't remember this part about a 30, 60, 90 triangle, you have a lot more review to do. The hypotenuse is double of the short side, which we already know that, right? The side length is x because it was an equilateral triangle where all the side lengths were x. So we kind of already knew that. And then this long leg is going to be the short side, but times square root of 3. So the total area of the triangle is going to be 1/2 base times height, which means 1/2 the total base, let's get it back, is x, times the height, which is, you can write this in a lot of different ways. I'm going to call it root 3 over 2 times x for a total of root 3 over 4 x squared. So that is the area of this triangular shape, this equilateral triangle. All right, so now we have an area of both components of the composite shape. But what we need to do is we need to maximize this, and we can only do that if we get this all in terms of one variable. So here we have the total area, which is what we want to maximize. And we need to put it in terms of just x. So now it's time to make a substitution to replace y, I should say, in terms of x. How are we going to replace y? Well, we need to use our constraint. Remember that 2y plus 3x equals 42, and the total perimeter is fixed at 42. Therefore, we know that 2y is equals to 42 minus 3x, and therefore y is equals to 21 minus 3 over 2x. This is the substitution that we need to use so that we can put our total area equation all in terms of just x. So the total area is going to be x times 21 minus 3 over 2x plus root 3 over 4x squared. Okay, now we're getting somewhere. We have an equation that's all just x's. Let's work this out a little bit because some things are going to combine in a way. We have 21x minus 3 over 2x squared, and then we have plus root 3 over 4x squared, okay? So that's two x squared terms. We have an x squared term there and an x squared term there. We can combine these together in a way that's putting this in standard form. So you need to notice this is now a quadratic equation, so we can put it in standard form and use the axis of symmetry to locate where a maximum or minimum would occur. And I'm actually going to confirm that this is going to produce a maximum, not a minimum. I'll show you why in just a moment. If we rewrite this with the coefficients of x squared, this would say rad 3 over 4 minus 3 halves. Those are the two coefficients on my x squared. I have a negative 3 halves and a positive square root 3 over 4. And then we have a coefficient of 21 on the x. Now this is a quadratic, right? It's like ax squared plus bx plus c. But this, if we get the same denominator, this is going to be rad 3 minus 6 over 4. And now hopefully it's very clear that this is going to be negative, because rad 3 is definitely smaller than 2. And if we subtract 6, then it's definitely negative. So this is negative. That means that the quadratic equation has a graph which is upside down. And there is, in fact, a maximum point somewhere. So how do we find the maximum? We have to use the axis of symmetry. Yeah, we're going to use the axis of symmetry equation, which says that the vertex of a quadratic function of the parabola occurs at a value of negative b over 2a, where my a, b, and c are the coefficients of the standard form quadratic. So that means that negative b is negative 21 over 2 times the a value, which is square root of 3 minus 6 all over 4. We're going to have to fix that just a little bit. Negative 21 over rad 3 minus 6 over 2, since those cancel. And we have a fraction on a fraction now, so we're going to want to flip the bottom to 2 over square root of 3 minus 6. Now this doesn't look that bad, but it also doesn't look that appealing, and a teacher of yours might gripe about having a radical in the denominator. If that's the case, remember that we just have to multiply top and bottom by the conjugate of this expression. Make sure you're multiplying the entire denominator. And this creates a difference of squares on the bottom, which is pretty convenient. Let's see, negative 42 times 6, of course, is going to be negative 252. And this is all going to be over 3 minus 36. So we have a negative 42 rad 3 minus 252 over negative 33. Let's get rid of the negatives, shall we? And let's also divide everything by 3. If we do that, we're going to divide everything by negative 3, that is. So we end up with 14 rad 3 plus 84 all over 11. This is our value for x that's going to produce a maximum area. Now, what exactly is this value? It's pretty hard to tell. I mean, you can approximate it. If you want to get this into a calculator, you can. Let's see. Rad 3 is like 1.732. So let's see if I can whip that up in a reasonable amount of time. Let's see. 8, 14, 29, 32. 7 and 7 is 14. And I think it should be approximately 24.248. So we're going to get that. We're going to add 84, and we're going to divide by 11. Still not the easiest task. I mean, you can, like I said, you can get a calculator. If you wanted to find out what the y value is, remember, you can use the substitution that we had. So you can use the fact that y equals 21 minus 3 halves x to say that this is approximately 6.2388. If we round it, let's say 239. This is in inches. This is in inches. I know they didn't ask us for the value of the side length on the left and right side of the rectangle. Where is it? They didn't ask us for the y value, but it's probably useful to have it there. And you can always check your answers by, seeing if we get 2 times 6.239 plus 3 times 9.8. What else was it? 9.84. Let's see if that does, in fact, give us approximately 42. Yeah, it gives us 41.9976. So we're looking good. We got the correct value so that this has a maximal area, this entire shape here. Okay, great. Now let's work on part B, which is actually a little bit easier if you know what you're doing. For part B, we want to find the length of side AE, which is just x again. Find a new value for x, such that the rectangle and triangle have equal area. So this one's a little bit different. We want to say that xy is equal to square root of 3 over 4x. And we get to, x squared, sorry. And we get to do something here that is not typical when we're solving equations. You have to mention that since x cannot be 0, we can divide both sides. In general, you do not want to cancel a factor on both sides when you're solving an equation because you might be eliminating solutions. But in this case, we know that x cannot be 0, so there's no risk of dividing both sides by x and causing a problem there. We should just say y equals square root of 3 over 4 times x. But at the same time, because of our substitution, we know that 21 minus 3 halves x is the same as y. So this one is actually an easier linear equation to solve. Maybe you wouldn't have expected that. Now, how would I solve this personally? I think I would multiply everything by 4. If I just multiply this by 4 and multiply this by 4, it cancels quite a lot. So we get 84 minus 6x, be careful with that, equals square root of 3x. All right, now let's move everything to one side that has x in it. And now we can factor out the x to reveal that 84 equals x times this quantity, root 3 plus 6, and therefore x equals 84 over root 3 plus 6, which again we can get fixed by multiplying the top and bottom by the conjugate. In case a teacher would gripe at this and not want a radical in the denominator, although I'll be fully transparent about this, once you get to the calc level, AP calculus, and even college level calculus, a lot of teachers really don't care if there is a radical in the denominator. They mostly just care if the value is going to come out to the same at the end of the day. So we end up with 84 rad 3 minus 504 all over negative 33. So here, again, the top part is a negative value. 84 rad 3 is somewhere around 150. So if you subtract 504, you're definitely going to get a negative on top, but that's okay because we get a negative on bottom as well. Let's simplify this by dividing everything by negative 3. And it turns out that actually works if we try to divide everything by, by negative 3. Let's see, we're going to get positive 168 minus 28 rad 3 all over 11. I'm going to do my thing again and try to multiply this efficiently. Let's see how it goes. 6, 1, 25, 29, 2, 74, and 6 is 8, 1. Okay, there we go. 2. So here we have 168 minus 48.496. And then we're going to divide this by 11. And what do you know? We get approximately 10.864. So this is what the side length needs to be in order for these two shapes to have the exact same area. That means that the y value for the rectangle would be 21 minus 3 halves of that, or approximately 4.704. So we're looking at a rectangle that's quite short, about 10 inches wide. There we go. And that equilateral triangle would have the same area as the rectangle. Okay, so these representations are heavy on the algebra. You really need to be able to understand from the words how to set up the situation, but especially from the questions, what is it that we're trying to maximize, or what sort of limitations do we have? Because limitations actually lead us to equations. Okay, I think that's enough blab out of me. I will catch you guys next time.